Hello everyone, I'm Miguel Otero. I work as a researcher in a technology center in Spain called AYMAR. Well, in first place, thank you to the organization for letting me present today. Today, I will present a study where we have established a procedure with a set of techniques that can help to predict the printability of cement materials. One of the problems with the cement materials, with the 3D printing of cement materials, is that there are no standards that establish how to characterize these materials and how to know if you have a printable material or not. So, during my presentation, I will address the following points. Firstly, a brief introduction about my company, AYMAR. Secondly, I will talk about one of the problems with the construction sector, that there is a sector so much polluting, and there is a search for a new ecological cements. Thirdly, I will talk about one of the changes that the construction sector has to carry out, which is the introduction of new technologies, smart and innovative, as the 3D printing. And then I will talk about characterization techniques that can help to predict the printability. These techniques can be divided into empirical evaluation techniques and advanced instrumental techniques. And then I will summarize the most important conclusion and next steps. So, my company, we are a technology center located in the northwest of Spain. We are dedicated to R&D projects, national and European. We have a staff of 300 employees, half of them in R&D positions. And our main capabilities are materials development, advanced manufacturing, sustainability, and process digitalization. I'm part of the advanced material group, where we have the research line of the building materials. Well, I will start my presentation by talking about one of the biggest problems of the construction sector, which is the carbon emissions that it generates, and is due to the use of ordinary Portland cement. So the construction sector contributes to the 8% of the global emissions, and well, the origin of these emissions is due to the OPC. You can see in the figure that the problem with this cement, with the ordinary Portland cement, is in its manufacturing due to the chemical reaction and the use of fossil fuels, and that generates a lot of CO2. So if we want to achieve the goals of the European Commission to reduce the carbon emission and to promote in circular economy, we need to use alternative cement. And what is where geopolymers came in? Geopolymers is a cementitious material that we research and vet in my company. And this material, this cement, is made from construction, is made from byproducts or waste. So obviously it's a more sustainable material and also shows some improved properties compared to OPC, like better fire resistance, better chemical resistance against acids, better mechanical properties, especially at early times. But obviously, the most important thing is the sustainability. This material has a 80% of reduction of CO2 compared to OPC. So in my company, we have involved in different geopolymer projects in 2015. We have collaborated with different institutions, different technology centers, universities, companies. We participate in European and national projects. And during our projects, we have validated the use of potential geopolymers in different applications in a relevant environment. I can highlight some of them. You can see in the figures, precast elements, facade panels, pavements. And in the last year, we have focused with these materials in two aspects. In one hand, the functionality. We tuned the formulation of this material in order to achieve specific properties, such as electrical conductivity, photocatalysis, thermal and acoustic isolation. And on the other hand, we have focused a lot in the 3D printing of these materials. In this case, we need to change the formulation so much. So the role of my company in our projects, well, we are basically a technology center, and we are formulation developers. We work at laboratory scale. So, well, We have a lot of experience in identify the most promising ways to create geopolymers. Then we apply a right conditioning and characterization. Once we have selected the waste, we start with geopolymerization. We use different alkaline activators, different admixtures in order to achieve a material with specific properties for a certain application. And for that, we have equipment related to manufacturing. We have also 3D printers and equipment to testing and analysis. So now I will introduce another change that the construction sector has to carry out, which is the implementation of new and innovative techniques such as 3D printing. Well, I will start talking about the problem with the forwards, with the casting process using forwards. This was the traditional casting technique since early times. In this technique, you have to use forward, which is made of rigid materials such as metals and timber. But this manufacturing technique has some disadvantages. It's a time-consuming. You need a lot of time to assemble the forwards. Occupational hazard. The laborers work in poor conditions under extreme climate conditions at high altitudes. It's a waste generator. The forwards has a limited useful life, and after that you have to discard them. And it's prone to errors. Errors might occur due to the molding, due to leaks, and so on. So on the other hand, we have 3D printing, which is a more innovative and smart technology and have some advantages compared to casting process. I can highlight some of them. Design flexibility. From a digital model, you can create complex geometries and customizable parts. On demand, you can address housing shortages, and you can adapt to various environments. You can reduce the human errors because you have an automation of the process. Cost efficiency because you have lower labor costs and a faster building. And environmental benefits because you reduce material waste and you can use sustainable materials such as geopolymers. I will explain the 3D printing process of the cements. Well, this process is broken down into 4 stages: mixing, pumping, extruding, and building. You need a formulation that can be pumpable until the printer, until the extruder. There, it needs to be extrudable smoothly through the nozzle with no clogging. And after that, the 3D cement needs to gain enough consistency to support the weight of the upper layers. And all of these stages are governed by rheology. But as I said before in the introduction, there are no standards that assess or that establish how to characterize the rheology or how to measure this. So that's one of the works that we carry out at AYMAR. I'm going to start explain some of the advanced characterization techniques to assess the rheology and to optimize the 3D printing process. To do that, we evaluate several commercial 3D printing samples, 3D printing cements. These 3D printing cements were supplied by our industrial partners, and they work perfectly right in the 3D printers. They are using to print houses, and we also, with our small printers, we printed these bases that you can see here. So we evaluate different samples that works perfectly fine with small and large printers. And the idea is to analyze different characterization techniques in order to obtain a protocol or database that can help us to predict the printability. So we can divide the techniques into empirical techniques. These techniques are easy to use, are low cost, and you can use on-site in the construction site. You can use to monitorize the process, the 3D printing process. On the other hand, we have advanced instrumental techniques. These are more precise, more sophisticated, but however, they are higher cost, and you can only use off-site at the laboratory for the moment. So I will start talking about the first empirical techniques. Manual extrusion. For this, you only need a mortar or silicon gun. And the idea of this is to evaluate the extrudability. If you can get a formulation that can get extruded through the gun, it's highly probably that the same formulation can get extruded through the printer nozzle. And also, you can assess the open time. If you can get a formulation that can be extruded over time with no clogging, so you can assess this open time. In the case of the 3D cement, you need at least 30 times of open time. The other technique is with the Vicat Needle. With this Vicat Needle, you can establish the setting time of the cements. This is according to a standard, and it's, well, in the case of the 3D printing, you have to adapt the test. And you can obtain the setting time, which is not the same of the open time. The setting time is more related to the buildability, and, well, is when your cement has enough consistency to support the weight of the upper layers. And in the case of these 3D cements, you need at least between 1 and 2 hours of setting time. Well, the other test, shape stability test. In this test, you have to put a load or a weight on the top of a sample, and you measure the vertical settlement. With this test, you can, again, assess the buildability, and it simulates the 3D printing. It simulates what the filament layers support with the weight of the upper layers. And the other test, the final empirical technique, is the flow table. This is a well-known technique with casting cements used to assess the workability, but we have to adapt to 3D printing. And in this test, you have to apply 15 shocks to a sample, and you measure the deformation, you measure the spread before and after the shocks, and it gives you a very precise idea if you have a printable material or not. And now I'm going to talk about advanced instrumental techniques. Well, in our company, we have a rotational rheometer. This is a very precise and sophisticated equipment. And with this equipment, you can measure the yield point, viscosity, thixotropic, which is very important for 3D printing, and the storage and loss modulus. These modulus are related to the solid and the liquid behavior, respectively. Some of the tests that we can carry out with this equipment are amplitude sweep, thixotropic test, and relaxation modulus. In this slide on the right, there is an amplitude sweep represented. In this test, we apply from a low to a high amplitude. We measure viscosity and the modulus. Well, there is a point where the modulus crosses, which is known as the yield point, and is the force that you have to apply a cement to start the flow. It's when the cement starts to behave as a liquid. And in the case of this 3D cement, you need to obtain a value around 900 Pascal. Another test that we can carry out with this equipment is a thixotropic test. Well, this is a very interesting test that can simulate the 3D printing process. You have 3 intervals. First interval is when the sample is inside the hopper. During this stage, we apply a low amplitude, a low deformation to the sample. Second interval is the extrusion process through the nozzle. We apply a high deformation. So you can see in the second interval, the red triangle means that it's related to the liquid behavior. So in the second interval, the cement behaves as a liquid. And finally, is the build up, is the recovery of viscosity. And during this stage, we apply a low deformation again. And it's necessary to obtain a high viscosity recovery in order to obtain a sample with a good buildability. And finally, the last test with the rheometer is the relaxation modulus. This, well, according to a criterion called Dalkey's criterion that assumes that the 3D printing lasts 1 second and you have to apply a deformation of 10 raised to 5 Pascal. You obtain a region called Dalkey's region, and if your relaxation modulus curve are inside this square, it means that you have a printable material. And in the case of these 3D cements, all the formulations are inside this square. Well, just to conclude, geopolymers represent a sustainable low carbon alternative to replace OPC and to achieve the goals of reducing carbon emissions and promote circular economy. The procedure that I presented today can help to predict printability of future cements. And these procedures will be used to optimize printable geopolymers in the following projects. Circulus project is an European project that the main objective is to obtain procedures to recycle construction and demolition waste and to find new added value for this construction and demolition waste, which is 3D printing. And the GEOS 3D project that we have to develop printable geopolymers from construction and demolition waste with acoustic and thermal insulation properties. And that's all for my side. Thank you very much. If you have any question. We are also at the 11:30, so we have a stand there. If you want to join us, come visit to us. You are more than welcome. Thank you.
Thank you very much, Miguel.
Thank you.
Any questions from the audience? We have 2 minutes. Good job.
Okay. I was fast.
What are you looking for here in terms of help with this project and help with the standardization? What do you think you'll be able to get from this show?
Well, the main problem with the 3D printing of construction of the cement is that there are no standards that establish how to characterize or how to know if you have a printable material or not. So if you want to optimize a printable material, you have to start from the rheology. You have to know about rheology, and I think with this test, with this characterization, we obtain a protocol that can help us to predict future geopolymers inks. Our main objective is to develop printable geopolymers, which are more sustainable than OPC. So yes, I hope that these techniques that can help it to achieve that.
Perfect. Thank you very much, Miguel.
Thank you.